Alright, so we are going to be working on partial fraction decomposition as a way to help us integrate functions. Let's go over the basics of partial fraction decomposition. Say we start with two separate fractions and then we get common denominators to make this into one fraction. When we use partial fraction decomposition, we are reversing this process. We can see that if we were to integrate this function, we could split it up into two separate fractions to make it easier to integrate. This is partial fraction decomposition. In this next example, it is important to notice that the degree in the numerator is smaller than the degree in the denominator. This is important because you can only use partial fraction decomposition if this is the case. Otherwise, you have to use long division before you can separate the fraction. So the whole goal of partial fraction decomposition is to see what a fraction was like before you multiplied it by the common denominator and made it into one fraction. So once you split up this example, you can see that you will have a over x, some constant over x, plus b over 2x minus 1 plus c over x plus 2. To then find these constant values, you want to first multiply everything by the common denominator and then plug in x values that will cancel out certain variables so that you can solve for each constant. We can then see that after solving for each constant, we can more easily integrate this fraction. Rather than having to integrate the fraction as a whole, we can integrate each individual part. Let's say we had a slightly more complicated denominator, for example, x times the quantity x squared plus 4. Since this cannot be factored further, you have to split the fraction up by writing a over x plus bx plus c divided by x squared plus 4. This is to account for the x squared in the denominator. You may also encounter a linear factor that occurs twice or 3 times. For example, in this problem, we have the quantity x squared plus 1 quantity cubed in the denominator. This means that you have to account for this linear factor 3 times. So we would have ex plus f over x squared plus 1 plus gx plus h over x squared plus 1 quantity squared plus ix plus j divided by quantity x squared plus 1 cubed. Alright, so let's look at a problem where you actually do have to use long division to solve. So in this problem, because the degree in the numerator is not less than the degree in the denominator, we first have to divide in order to integrate. So after doing long division, we can see that we're left with 1 plus a remainder that has a smaller degree in the numerator than the denominator. From here, we can see that our denominator of the remainder actually doesn't factor. So we have to use completing the square in order to factor. And then from here, we can see that this problem becomes a U sub rather than a partial fraction decomposition problem. We know this becomes a U sub problem and not a partial fraction decomposition problem because the denominator is not a product of two functions. So let's look at a much more complicated example. So from what we've learned, it's pretty easy to split up this fraction into a over x plus bx plus c over x squared plus 1 plus dx plus e divided by quantity x squared plus 1 squared. After multiplying everything by the common denominator, we can see that we would have trouble using the normal method of just plugging in x values to cancel out certain variables. With this problem, however, we can't do that, so we're going to have to use a different technique. We want to first start by factoring everything out. We then want to group together our constant values with their corresponding variables. For example, a and b both have an x to the 4th power, so we can group these together and say quantity a plus b times x to the 4th. After we do this, we can compare our right side of the equation with the left side of the equation. So if we look at ax plus b times the quantity x to the 4th, we can see that on the left side of the equation there is no x to the fourth variable. So that means that a plus b, the constant in front of x to the fourth, has to add to equal 0. We then look at the next variable, cx cubed. On the left side of the equation we have a variable negative x cubed, so that means that our c value has to equal negative 1. We can use the same process with the rest of the variables. After we have set up equations for each of the variables, we can start to solve for each of these constants. We can see that we already know the values of c and a, so we can use these and plug them into our other equations to solve for the remaining variables. After we have found each of our constant values, we can simplify the fraction so we can more easily integrate. So we would have 1 over x minus x plus 1 over x squared plus 1 plus x over x squared plus 1 quantity squared. We can then separate this integral even more. Notice how we can separate x plus 1 divided by x squared plus 1 into x over x squared plus 1 and 1 over x squared plus 1. In order to integrate x plus 1 over x squared plus 1, we must do this separation. We can then see that this becomes an easy problem to integrate. Let's look back on what we did in that whole problem. So we started out with a function and we separated it into smaller fractions and tried to solve for our constants, but we found that we couldn't plug in x values that would make variables cancel out, so it was harder to solve for these constant values. To make this problem simpler, we grouped our constants with their corresponding x values. From here, we set up equations corresponding to the left side of the equation. After solving for our a, b, c, d, and e, we were then able to split up the integral and more easily integrate. After learning the technique of partial fraction decomposition, it is really easy to get in the habit of integrating any function using partial fraction decomposition if the function has a denominator that can be factored. The problem with this is that oftentimes, even if the denominator is factored, it is much easier to use u substitution rather than going through the process of partial fraction decomposition. It is always a good idea to start by using u substitution rather than going straight to partial fraction decomposition, because partial fraction decomposition is a much longer process than if you could just do a simple u substitution. Alright, so let's look at a little review. So the first step when you're trying to integrate a function is to try u substitution before even attempting partial fraction decomposition. To the left, I have listed some key ideas about partial fraction decomposition. These are some of the most common forms of denominators that you will see in these types of problems.